Okay, now things get interesting. In the ISAM, we couldn't do insertions other than using overflow pages. In the B plus tree, this gets much more elegant. Let's start with a simple case. We're just going to insert 25 into this little B plus tree we have here. We start by finding the correct leaf for the new item. So that's just a search in the tree, and we find the right leaf. And then, since there's room in that leaf, we simply put 25 into that leaf. That's fine. That works just like ISAM. Of course, as with ISAM, we want to keep the leaf sorted. So in memory, while we have the leaf in the buffer pool, we'll sort the entries. Now let's look at a more interesting case. We want to insert 8 into the same tree. All right, and we find the leaf where it belongs, but that leaf is full. So when we get down there, we're going to split the leaf node if there's not enough room. So there's no room for 8, so we're going to split it. By which I mean we're going to add a new node to the tree, a new leaf node, and we're going to redistribute the values that were on the old leaf node, as well as the new entry 8, across both. So now you can see we have the lower valued items in the old leaf node and the higher valued items in the new node. And because there was an odd number of values, we decided to put 3 on the new node and leave 2 on the old node. And that'll be a convention we'll follow when we do splits. So now we can see we have a new node to link into the tree. So we need to fix those next and previous pointers so that new node is in the linked list at the bottom of the tree. So we update those pointers on the neighboring pages, and now we're all linked into the leaf level. All right, but we're not quite done yet. Something's wrong. The insertion algorithm's not complete. What's wrong with this picture? This node's an orphan, okay? By which I mean it doesn't have a parent pointing to it, and we need to fix that. So we're going to create a parent. It's going to be a new index entry, and it's going to point to this node, and as a split key, as a value in that index entry, we're going to take the lowest value on the page we're pointing to, because everything on that page is greater than or equal to that value. In this case, it's 5. Everything on that page is greater than or equal to 5. And now we want to put that new index entry into the parent of the original node. The problem is, in this case, is that the parent itself is full, and so now recursively we're going to split the parent. As an aside, in this example, the parent is the root, which is a special case, and we'll be dealing with that shortly. But right now what we're going to look at is what would happen splitting any full parent in the tree. All right, so we need to get this 5 index entry into this node, and the node is full, so we're going to split it. So we create a new internal node, and we're going to redistribute the rightmost d+1 keys over to the new node. And we're going to leave d keys, which in this case is the new index entry as well as one of the old index entries, into the left-hand node. So we've got 3 on the right and 2 on the left after redistribution. Now we're going to need to insert something into the parent to point to the new node. An index entry has to go into the parent. Which index entry should it be? Well, again, we want it to be the smallest value on the right-hand side, which in this case is 17. All right, so we're going to put the 17 up in the parent. But unlike in the case of the leaf level, the 17 is going to actually get pushed up into the parent, not copied up. So the 17 is now up above, and you'll see that we have the right number of pointers and keys in the nodes that remain. And now there's room for us to put 5 on the original node. So we can do that as well. Okay, now here's a note. When we split the parent, in this case, it was the root. So we had to actually allocate a new root to hold the parent of the right-hand side of the split. And this is a rare event in a B plus tree. It happens when your splits bubble all the way up to the root and the root itself is full and has to split. It's exactly what happened in this example. And you simply allocate a new root and the tree grows by 1 level. And so now we have a B tree of height 2 instead of height 1. Major thing to note here is the distinction in splitting a leaf versus splitting an internal node. The key distinction is that splitting a leaf, we copy the key up. So you'll see the 5 remains as a data entry at the leaf level, as well as being copied into an index entry up above. By contrast, the 17 was pushed up from the middle level to the top level. Okay, so this is the final B plus tree after the split. And let's check our invariants to make sure that we believe that it's right. The key invariant is one that we inherited from the ISAM. It says that if we have a key KL in a node, then all the things to the right of that key, all the things down the pointer PL, are greater than or equal to KL. So for example, everything to the pointer to the right of 17 should be greater than 17, and it is. And if you inspect the rest of the keys in the tree, you'll convince yourself that this is true in our example. How about our occupancy invariant that we added for the B plus tree? Is it true that every node other than the root has at least half of its entries full? So its number of entries between the order D and 2D. And you can see that's true as well. There's at least 2 items on every one of these nodes.